Hello everyone, today let's take a look at Quantipus number 99, a question about independence where two dice are rolled, and then we have the following three events, A, B, and C, and it's asking us a bunch of questions about them. So in part A, what's the probability that the sum of the two dice equals 3? That's event A, given that the first dice shows a 1, that's event C. Okay, so if we condition on the fact that the first dice has to be a 1, well then the second dice has 6 options. So that means there's 6 total ways for the first dice to show a 1. Now, how many of these combos have a sum of 3? Well, this dice is going to need to have a value of 2 for it to sum to 3. There's only one way to do that, so the probability is 1 out of 6 here. This on the denominator is the magnitude of C, and this on the numerator is the magnitude of A intersection C. So you may have also decomposed this formula into the probability of A intersection C over the probability of C. But we know that this over here is just the same thing as this, right? If we had the probability instead, well then we'd get 1 out of 36 on the top, and we'd get 6 out of 36 on the bottom, and then they just cancel out and we'd be left with 1/6. Alright, so now let's move on to part B, asking us what is the probability of B given C? So event B is just that the sum of the dice equals 7, so we're going to do pretty much the same thing. So again, when we restrict our sample space to C, we make the first dice 1, well then the second dice has 6 options, so again 6 total options. Of those, one of them makes the sum to 7, and that's when this dice is actually a 6, so 1 out of 6 again. Okay, so now the interesting part. Let's go to part C. Are A and C independent, and what about B and C? Well, the definition of independence is just basically that the probability of A given some event happening C is just equal to the probability of A happening itself, right? So if A and C are independent, that means that if we condition on C, the probability that A will happen is the same as if we didn't condition on C. So another way of putting this, well, we know that this is just equal to P of A intersection C divided by the probability of C by the definition of conditional probability. And if we set that equal to the right-hand side, then we can also see that if the probability of A intersection C equals the probability of A times the probability of C, well, then also this means independence. Most of the time people say things are independent by showing this, but this makes a lot more sense, right, intuitively. So now let's actually look at the A and C in our example. We already calculated the probability of A given C, and it was equal to 1/6. So now we ask ourselves, is this independent of C? Is this equal to the probability of A? So A was the event that the sum of the two dice is 3, so what's the probability of that? Well, there are 36 ways to roll 2 dice, and only 2 of these ways sum to 3, 2, 1, and 1, 2. So there's a 2 out of 36 chance that the sum of 2 random dice is equal to 3. So this is equal to 1/18th. So does 1/6 equal 1/18th? Obviously not, so A and C are not independent. All right, now let's check if B and C are independent, the other part of part C. So again, we ask ourselves, is the probability of B given C equal to the probability of B with no condition? Well, we already calculated the probability of B given C in part B, and we got 1/6. So B is the event that the sum of 2 dice is 7, so we have 36 ways to roll 2 dice, and how many of them sum to 7? Well, we have 5, 2. 2, 5, 3, 4, 4, 3, 6, 1, and 1, 6. So that's 6 ways. And then look at that, 6 on 36 is equal to 1/6, which is equal to the left-hand side of our equation. So are B and C independent? Yes, they are. So B and C are independent, but A and C are not. But let's visualize what this actually means with some Venn diagrams. So I have some probability space with the event A, the probability that the sum of 2 dice equals 3, and event B, the probability that the sum of the 2 dice equals 7. Obviously, there's no overlap here because the sum of 2 dice cannot be 3 and 7 at the same time. And now my event C is that the first dice is a 1, so let's draw that in here. You can see there's some overlap with B because both of these could happen at the same time, and same with A. So we found that B and C were independent, right? So what does that actually mean visually? So we're saying the probability of B given C, which is going to be this blue part divided by the sum of this green part, well, we're saying that's equal to the probability of B, which is just the entirety of the B circle divided by the magnitude of the entire probability space we can draw as this box. So in our case, the magnitude of the whole probability space was 36, right? There's 36 ways to roll 2 dice. And there's 6 ways that these dice could sum to 7, so the magnitude of this red area was 6. Now there's only one way that the dice could sum to 7, and the first dice would be a 1, right? So this magnitude is 1. And the magnitude of the green circle was the number of combinations of 2 dice, where the first dice is a 1, which we got was 6. So you can see the probability of B originally was 6 out of 36 equals 1/6, and the probability of B, given that we're in this circle C, is also 1 divided by 6. So that tells us that the events B and C are independent, which means knowing something about one of them does not change the probability of the other one happening.